Okay, so this is the stopping distance task, which was based on the visit to the computer room where we use this simulator to create some data all about stopping distances. So you might recall that in order to use the simulator, I asked you to decrease the speed down to 25 miles an hour. Okay, to start the car, as soon as you see the car arrive on screen, you click the stop button. Okay, and it's taken a while to arrive, so we click the stop button, and we got this data of our reaction time, the reaction distance, the braking time, and the braking distance. And you repeated that for a range of different speeds in order to create a data table from which then we can plot a graph using Excel. Okay, and based on all that, we produced this worksheet. So we've got here, first of all, a graph of the reaction, the braking, and the total stopping distance of a car at a range of speeds. So this is the distance over which it takes to stop at speeds starting at 30, going up through to 90 miles an hour. Okay, so because this is a black and white graph, perhaps the colour has been lost, but we can see here that the reaction distance is the little triangles. Okay, and going along the bottom, the reaction distance increases ever so slightly as we go along the graph. The braking distance is the squares. Okay, so the braking distance is this relatively steep line. Okay, so we can see that the speed of the vehicle affects the braking distance quite drastically. And then the total distance is obviously the combined distance that the vehicle takes to stop, the reaction and the braking combined to make the stopping distance. Okay, the graph at the bottom of the page was the similar sort of thing, but this time it's the times. Okay, and we can see that it's very similar to the first graph, with one important difference: is the reaction time remains pretty horizontal. So the time it takes a driver to react remains the same, but if you're going faster and faster, that translates to greater distance on the ground. Okay, because your car is traveling faster and faster, so no matter how quick you are, it will travel further before you can actually get your foot on the brake. So we've got here a copy of the data that was used to create those two graphs. So it says here, look at graph B. What do you notice about the reaction time across the range of speeds? As we've already mentioned, on graph B, the reaction time stays constant. Okay, so the time that the driver needs to react remains constant. Okay, and why is this? Well, this is due to the biology of the driver. Basically, is the driver themselves reacts consistently quick, no matter what the situation. So, if we did an experiment to compare different drivers, we would find it's different for different drivers. However, an individual driver would have a reasonably consistent reaction time across all those speeds. It then says, look at graph A. What do you notice about the reaction distances? Okay, so as we've already mentioned, these do increase slightly. So these increase slightly. As speed increases. And this is because the faster you're going, the faster you travel, the further you move over a fixed time. So the reaction time is fixed, but if you're traveling fast, then you will travel further than if you are traveling slowly. Okay. Right, look at graph A. Do you notice anything odd about one of the results? So this is not so much a physics question as a data analysis question. Okay, so this data here is clearly out of place. This data would be described as anomalous. And in the instance of the simulator we used, I suspect that the person who created this data accidentally recorded the 80 mile an hour data when they actually set the simulator to more like 70 miles an hour. So it's probably an error on the part of the operator. But it's important that you can recognize anomalous data across all your science exams. Okay, so we could say anomalous data. And operator error, which is easily done when you're doing a very repetitive task like setting the speed, recording the time and distance. Okay, highlight the data on results table C. So if we just quickly look back, we'll notice the data is at the 80 mile an hour setting. So if we look across 80 miles an hour, okay, and we're looking for the reaction distance. Okay, so it's the distance we're looking for, 80 miles an hour, distance, these values here and here. Okay, so it dips down again from the 285. You would imagine this value to be somewhere between 285 and 236, but it drops back down again. It then says, look at the line of best fit for the total stopping time on graph A. Do you think that a straight line is the best choice? Okay, so if we look at the data here, the computer has plotted a straight line, but if we look closely, it is actually a very gentle upward curve. So there is a sort of an exponential nature to that line, exponential element to that line. So possibly a curve like that would be more appropriate in this case. Okay. So it says to draw a better line of the best fit on the graph. Remember that at 0 miles per hour, the total stopping distance will be 0, not a negative distance. So what that's referring to is the fact that when you draw a line of best fit, it should start at 0, because at 0 miles an hour, you don't need, and join up with your curve there. Okay, so it's a curve. That's, given that I did that on later, it doesn't look quite right, but you can see the general idea there. Use graph B to find out the braking time and stopping time for this car and driver at 20 miles an hour. Use a ruler to show how you did this on your graph. Okay, so at 20 miles an hour, and that's a speed that we didn't ask the simulator to give us. So we're going to use the graph as a tool to find out something we don't already know. Okay, unfortunately the photocopying hasn't helped us here, so I've drawn a line at 20 miles an hour, and then, being as accurate as we can, I'm going to rule across to the time axis for those two values. So this one here I would suggest is 1.1 second, whereas this one is more like 1.4. Okay, so it's a bit higher. So the braking time is 1.1 seconds, and the stopping time is 1.4 seconds, according to the graph. Okay, it says use the knowledge organizer to answer these questions. Okay, now the knowledge organizer does appear in our boards. Okay, so if we go back to here and we look at our boards, then zoom out, the knowledge organizer for each of the topics in your exam is over to the left hand side here. So this is Newton's laws over here. So this is the knowledge organizer. Oh, sorry, wrong one. Here we are. This is the knowledge organizer we need to refer to. Okay, so basically the question is based around this table. Okay, so you need to state what factors affect the thinking distance and the braking distance. Okay, so the thinking distance is heavily influenced by the speed you're going at. We've already mentioned that, but also alcohol and drugs, tiredness, mobile phones. Okay, so if you're tired, your reactions are not as good as they should be, and obviously mobile phones, people are very distracted when they're using mobile phones. And then the braking distance is more to do with the mechanics of the vehicle or physics of the environment, really. So again, the speed is a factor, But the road conditions, is it slippy or otherwise? The mass of the car, but it should have an extra S in there, so a heavier vehicle will take more energy to stop, and therefore will have a greater braking distance. Condition of the brakes, okay, so if your brakes are worn down, they won't be as effective. If your brakes are hot, they won't be as effective. And then the condition of the tyres, okay, if your tyre's not gripping the road appropriately, then obviously you run the risk of skidding, and skidding actually makes your stopping distance longer or your braking distance longer. Okay, so those are all factors that would affect your stopping distance in total. If you break it down into those two different distances there. Okay, and then if we move over here, this is a question taken from a GCSE paper. It says a car is moving at a speed of 15 meters per second. A child runs out into the road, causing the driver to make an emergency stop. The graph shows how the speed of the car changes from the moment the driver sees the child. Okay, so the child pops up into the road here. Okay, that's my best picture of a child there. The driver sees the child, but then takes a certain amount of time to actually react. Okay, so if we come down there, we'll notice that that's 0.8 seconds. So the reaction time there is 0.8 seconds. So that's what we need to write here, 0.8. Okay. And part two, how long did it take the car to stop once the brakes were applied? So the brakes were applied here at 0.8 seconds, and the car came to 0 meters per second at 4 seconds. Okay, so 4 seconds take away 0.8 seconds equals 3.2 seconds. Now it says use the equation. Start again. Use an equation from page 2 to calculate the deceleration of the car. Now we don't have a page 2 here, but we've done a few acceleration calculations recently, so we should know that it's the change in velocity divided by the time over which that takes place. Okay, so in this particular instance, the car is doing 15 meters per second at the start of the braking, and is doing 0 meters per second once it stops. Okay, so the change in velocity is therefore 15 meters per second, and we've already calculated that that happens over a period of 3.2 seconds. Okay, so that's 15 meters per second divided by 3.2 seconds, and that will give us value in meters per second per second. Okay, so if we so we're going with 15. Let's clear the calculator and let's go full screen. So 15 divided by 3.2. Okay, it's 4.6875, which we can round up to 4.7. Okay, so that's 4.7 meters per second per second. Now, as it's decelerating, we might want to put a minus sign there just to be sure that it is a deceleration. And the final part of the question asks us explain how the graph would be different for a driver who had drunk alcohol. Okay, so rather than explain, it might be better to actually draw it on there. So a driver who's drunk alcohol, their reaction time would be affected, it would be longer. So we might see this sort of thing, that the graph comes out to here or even here, but then the actual braking time, assuming that the drunken driver hits the pedals appropriately, would be pretty much the same gradient, same angle, but that would mean that the overall stopping time would obviously be longer. Okay, so it's this portion here of the graph that is affected by the alcohol, because the reaction times would be slower. Okay, so you can write an explanation there, but it would be a good idea, I think, to use the graph to illustrate your explanation. Okay.